Good morning. Today we'll be solving question 2d from the exam preparation sheet 4 in the control system module EG243. This is a typical question where we have a block diagram. It's a closed loop system with an inner loop within the outer loop. And the question is asking us to find K1 and K2 to yield a peak time of 1 second and a settling time of 2 seconds. If we want to interpret that in the time domain, what that implies is that if we have the time response of the output, if we have our first response or our first output, let's say is 1, if that is 1 second, it means that the time it would take to reach the maximum peak as this oscillate and settle, this maximum time, this time should be 1 second. And the settling time, if we're assuming our 5% tolerance criteria, then this time should be 2 seconds, where this is t in time, and this is your c of t, which is the output of our system. Of course, we have it here in the Laplace domain. Now, to solve this, the first thing we need to do is to reduce this block diagram into a more simplified form. In other words, what we want to achieve is to have one input r of x, and this should feed into one transfer function, in this case, t of x, to give us one output, which is our c of x. And what this means is that our output, which is c of x, it's r of x multiplied by the closed loop transfer function, in this case, which is our t of x. Therefore, it means that the closed loop transfer function of this system, it's the output c of x over the input r of x. Okay? And the first thing to do is to simplify the inner loop. So we need to simplify this inner loop to have one transfer function. And to do that, if we simplify the inner loop, okay, let's call this, since this is a feedback, from the output, let's call this H1. Let's call this G1 of x. Of course, they are all in the S domain. So that means that the closed loop transfer function T1 of x in the S domain is going to be the forward path transfer function G1 of x all over. Of course, we can see here in this case that this is a negative feedback system. So that's going to be 1 plus G1 of x multiplied by H1 of x. And all we need to do is to substitute in the transfer function for G1. We can see in this case it is 50 over x into x plus 1. So this is going to be 50 into x plus 1, all divided by 1 plus 50. Again, our G1 x into x plus 1, all multiplied by H1 of x. In this case, our H1 of x is K2 multiplied by x. And if we do the simple maths, just rearrange this and simplify this, the solution will come up to be 50 over s into s plus 1 plus 50 K2 of x. Okay? Okay, so now we have one transfer function. We can now call this our T1 of x, which is the overall transfer function for the inner loop. And now we can now use that together with K1, which could be some control action, to get the total transfer function for this system. And of course, it means that this becomes the forward path transfer function, which is g of x. And in this case, the feedback part, h of x, is equals to 1 because it is unity. We don't have any transfer function on the feedback part. So therefore, the overall closed loop transfer function, if we call this, in this case, t of x, will now be g of x, which is the forward path transfer function, all over 1 plus, again, this is negative feedback, so that becomes plus gx multiplied by hx. And of course, since hx is equals to 1, we can write this as gx over 1 plus gx. Okay? And all we need to do is to substitute in our gx, which is basically k1 multiplied by t1 of x. And if we do that, it means, therefore, that our t of x becomes, if we substitute this in, we should end up with 50 k1 over s squared plus 1 plus 50 k2 multiplied by x plus 50 k1. Okay. Now, looking at this, of course, it is a second order transfer function. We can't compare the t of x to the generic second order transfer function, which is omega n squared over s squared plus 2 zeta omega n x plus omega n squared. Typically, you will have this formula in the formula sheet. We know that omega n is the undamped natural frequency, and your zeta is your damping ratio. Okay, and of course, if we compare this, our generic CS, or a generic closed loop transfer function, if we compare the s raised to power 2 term, we can see that the coefficient is 1, which is the same. Now, we can generate some equations from this. First of all, if we look at the s raised to power 1 term, we can see that 2 zeta omega n, in this case, is the same thing as 1 plus 50 k2. Okay, let's call this equation 1. Okay. Similarly, if we compare the s raised to power 0 term or the constant term, we can see that in this case, our omega n squared is the same thing as 50 k1. Again, let's call this equation 2. Okay. And also, if we look at the question from the start, the design criteria that was given to us, we are given that the peak time, which we represent as TP, the design criteria is to make this equals to 1 second. And if we look at our formula sheets, we know that the peak time can be represented as pi over omega n, the square root of 1 minus zeta squared. Let's call this equation 3. And finally, the settling time. From the question, the settling time Tx, the design criteria is to make this equals to 2 seconds. And if we look at our formula sheet, this is the same thing as 4 over zeta omega n. So we can call this equation 4. So now we have 4 sets of equations to simplify. And if we solve this, we should get a value for k1 and k2. And that would be our next task. Okay, so now we have 4 sets of equations, and all we need to do is to solve those equations to get values for k1 and k2. And the trick is to find the value for zeta and omega. In this case, if we look at equation 3 and equation 4, we can divide equation 4 by equation 3. And of course, if we look at the right-hand side of equation 4, we have 4 over zeta omega n, all divided by the right-hand side of equation 3, which is pi over omega n into 1 minus zeta squared. And if we look at the left-hand side of equation 4, we have 2. And if we look at the left-hand side of equation 3, we have 1. So we have equation 4 divided by equation 3. If we simplify that, we should have 4 omega n into 1 minus zeta, square root of 1 minus zeta squared, all over zeta omega n pi. And of course, 2 divided by 1 should be equals to 2. So therefore, as we can see, in this case, your omega n can cancel out omega n, and then we are left with 4 over pi. And then we can move zeta into the square root. If we do that, we should have 1 over zeta squared minus 1. And this should be equals to 2. Okay? And if we move the 4 over pi to the right-hand side, then we are left with 1 over zeta squared minus 1 should be equals to 2 pi over 4. Okay? And if we solve this, make zeta squared a formula, we should arrive at zeta to be equals to 0.537. Okay? So that's our value for zeta. And then next, we substitute the value of zeta that we've just calculated into equation 4. And if we do that, we should, into equation 4, if we do that, we should have a value for omega n. So omega n is equals to 4 over 2 zeta. And we know the value for zeta, so omega n should be approximately equals to 3.7224. Okay? And then moving on, since we know the value for zeta and omega n, we can now, if we go back to equation 2, from equation 2, we know that in equation 2, our omega n squared is equals to 50k1. And since we know a value for omega n, which we just calculated from here, we can substitute omega n. So in this case, our k1 is equals to omega n squared over 50. And if we put the value for omega n, our k1 should be approximately equals to 0.2774. And finally, if we go to equation 1, so from equation 1, in equation 1, we have 2 zeta omega n to be equals to 1 plus 50k2. If we make k2 subject of formula, k2 subject of formula, this should be equals to 2 zeta omega n minus 1, all divided by 50. And if we substitute the value for zeta and the value for omega n, our k2 work out to be approximately equals to 0.06. Okay? So we've succeeded in calculating the value for k1 and k2 based on the design criteria. So that ends the solution for this question. Thank you.